We're going to look at these power series and something that we call the interval of convergence of these power series. In essence, they represent the domain of these power series functions. These intervals of convergence of these x minus c to the power n power series, type power series, have some parts to it. The C represents the center of convergence. That horizontal shift, which is exactly what it is, it's just like the horizontal shift for parabolas. That horizontal shift of C represents our center of convergence. Now, the distance from the center that the series converges is what we call the radius of convergence. So that's R. So using the center and the radius, we can start getting an interval of convergence. Now, the radius of convergence comes from our ratio test. Okay, so this radius of convergence, R, we generate this from the ratio test. So this is going to come from our ratio test. Now, when we do this, the power series has three possibilities. It only converges at the centers. That means that it's only good at that one point. Okay. The series can converge for all x, and this could be when the radius is infinite. Okay. There's some power series for which the radius can be infinite. And then the radius convergence can have some specific radius. And that specific radius can be found from our ratio test. And our ratio test for this specific one, for this particular example, the first one we've given here, the radius is 1. For this particular one, because this is generated from the ratio test, where an over bn must be less than 1. So this is how we determine the radius. Okay, now that the radius can extend once we start introducing the an terms to these power series, but this is essentially how it works. So we have a center, we have a radius, and that radius we generate from the ratio test. Now, when we talk about the last part of this interval, there is the endpoints of the interval. So we can have our radius look like this. So we have our center, C. We have our radius, R to the left, and R to left and right. That would represent our R. And then we have these endpoints. These endpoints are what we then need to consider for the last part of this, the interval of convergence. So the interval then is going to be whether we include the endpoints, we have them closed like this, or we don't include the endpoints like we have on the left. And so we have some terminology that goes with this as well. So we can have half open, so we can have it equal to one side. Sorry, we can have it open, where it's open on both sides, so it's not equal to on the left side and not equal to on the right side. So that would be a situation where our endpoints look like this. We have these open endpoints here and here. Okay, so this is what we call open. This is an open interval. This is also indicated by these curved brackets on both sides. The other situation we can have is a half open, where we have open on one side and closed on the other. So open and closed, which would be, we would just fill in one endpoint. We include the endpoint on one edge of the radius. And then the third situation is we can have it fully closed. So we can have it equal to the endpoint. Our domain is equal to the endpoint on both sides. We close it on both, and then it would be closed on both ends of that radius. Okay, so this is essentially what we're going to do. We're going to, first of all, establish our center by just looking at it. We can see our center by a horizontal shift. We're going to use a ratio test to work out the radius of convergence. That just tells us how far from the center we're going to use. And then lastly, we need to test the endpoints. And we're not going to use necessarily a ratio test for the endpoints. We will use some other tests, often use some other tests to test to see if the endpoints converge or diverge.